Hi class, welcome back to Electromagnetics. Today we're going to continue our review. Before we get into the meat of things, we're going to talk about scalar and vector fields today. First, I'd like to start with inspirational thought. It comes from Exodus 35:35. There we read, "He has filled them with skill to do all kinds of work as designers, all of them skilled workers and designers." So this is taken from the story of when they were about to design and build the tabernacle, and so it's clear here that uh, some of the designers were filled with the Spirit of the Lord and to do that type of work. And so, to me, this has always been a meaningful verse in that I do pray that God would infill me with that I could be empowered to do design, and that it would inspire my design. And I feel like it has been done in the past, and you too, as well, can be indwelled with the Spirit to do that, and should ask the Lord for that. He would. It clearly says here that He does do that. So again, looking at our outline, we've talked about vector algebra, we've talked about our coordinate system. So again, this will get us halfway through this first part with looking at scalar and vector fields. So we want to start this conversation by talking about some definitions. So the first thing is, what is a field? So a field is a mathematical mechanism used to characterize a phenomenon over some defined space. Basically, it is a mathematical function that is typically associated with or accurately describes a phenomenon over space-time. And so some examples of these types of fields would be like a gravitational field. It's acting on different things at the same time in different spaces. And same thing can be said for electromagnetic fields. So let's look at the different types of fields we can have. We can have a static field. So in a static field, the values in the field are relatively constant. For example, gravitational fields. Gravity is basically the same uh, anywhere you go, at least in a closely defined area. You can have a varying field. So values in this type of field are always changing. So an example of this would be like a temperature field. Like if we derived a function for a field in a room that told us the temperature at any point at any time, that could be a varying field. We can have scalar fields. So values in this type of field have only a magnitude. So again, that temperature field would be an example of that. Then you have vector fields. So these values in this field have both a magnitude and a direction. So these are where we're headed. Electromagnetic fields are going to be vector fields. So let's look at some examples real quick of different types of fields and how these mechanisms work. A good 2D example to start off with would be a field that describes the height of a cone on the surface. So we could give a single value for a specific point on the cone, or equation that does that. But using the field approach, we can now characterize the height for just an entire field of points at one time. So we can do this by defining the height in space relative to position as defined in our coordinate system. So we'll be dealing with the Cartesian coordinate system. And to do that, we can do it as simply as this equation here, where on the left, that's just saying that height relative, or in terms of an xy position, is going to be equal to the equation on the right, 6 minus 2 times the square root of x squared plus y squared. So taking this equation and using this, we've created a height field. And so this is what's used to describe the situation going on with the height. So let's ask ourselves some basic questions. Is this field static or varying? Well, since the height doesn't change over time, if I go and examine it at one xy point, then come back later at the same xy point, that height's going to be the same both times. So that's what we call a static field. So this is a static field. Is the field scalar or vector? Well, the height is a directionless quantity, right? It's not like height in one direction or another. So that being the case, this would be a scalar field. While we can add a third axis for height, we can also graphically represent this field in 2 dimensions using what's called a contour map. This is a very common approach. So examples of the 2 ways we could represent this. The first is by adding that third axis like we said, so you can see this equation here defines all the points on this cone as long as x and y are both less than or equal to 3. We can also do a contour map like this one here. So this is like looking from the top down, and you can see at each line that tells us, what the height would be. So the height's the same all the way around on these lines. So we're at 4 all the way around. We're at 2 all the way around. So this is a contour map. A 3D example that we can look at is to characterize the distance in a room from the origin of the corner. Again, we can give a single value for a single point, but again, we want to characterize the field of points in a room. So we do this by defining the distance in space relative to a position defined in our coordinate system, and we'll just arbitrarily pick one corner and make it the origin. So when we do that, we can use a function such as this one, whereas r, which will be our radial distance to the point, in terms of x, y, and z is just equal to the magnitude at that point relative to an origin. So again, if we look at this example, we have our definition of our field here. So using this function right here, we've again described a distance field, so the distance from the origin to describe this situation. So again, we'll ask these questions: is this field static or varying? Again, if I go back to an XYZ point and then come back later to the same XYZ point, it'll be the same. So it is still static. Is it scalar or vector? Again, this distance will always be the same, and it doesn't have a direction associated with it, so it will be scalar. So we can again graphically represent this using a contour map. However, since it is a 3D field, we must use a 3D contour map. Or again, we can take 2D slices through the map for different views, which is common in a lot of applications. So here's the 3D representation of that. You can see the point, at any point we'll have a radial arm going out to that has an x and y component associated with it and a z component. We can have the contour maps as well. Here we could take a slice. If we were looking just from this direction, that would be our contour map, or straight down the floor would be, so on. The previous 3D example, again, can be extended to include temperature at each point in the room. So here, since the temperature can and probably will vary over time, the new function now has an added dependent variable. We had x, y, and z before, but now we're going to add a new variable t for time. And so this is the function would be represented by something like this: t at x, y, z and a certain time. So this new temperature field can still be expressed using a contour map. However, it's going to require multiple maps, with each map showing the isothermal curve in the room for each increment of time. So all the previous examples so far have been scalar fields. That is, they have only characterized magnitude values. This concept can now be extended to include vector fields, in that each magnitude now has a direction in space associated with it. This can now be expressed mathematically using the unit vectors we've talked about before, ax, ay, and az, and their corresponding components. And so the function would be in this form. So we'll have our function vector field here, and then you can see there's the magnitude, and it's going to vary over x, y, z, and t for x, and for y, and for z, and then in the associated directions. So you need to note here that this can also be done in cylindrical and spherical systems as well. But the tricky part here is that the unit vectors in these systems are generally functions of the coordinates as well. So the direction vectors are going to change with position as we move around. Remember that r d theta component like we talked about earlier. Vector fields can also be represented graphically using contour maps, and we do this a lot. But efforts have to be made here to also represent the direction at each point along the magnitude. So a couple examples of what this looks like are given here. So here you can see again the magnitude will be the same all along this circle. However, at each point you can see the direction is different and is varying. So this is very typical contour map for an electromagnetic field. You can also see it this way, where again the magnitudes are the same, but the direction is always going to be tangential to the circle, which is kind of the same thing that's going on over here. So this wraps up our review of fields. Hopefully this isn't all totally new to you, but it's just a little bit of review. Maybe the concept of vector fields might be extending you a little bit, but as we get into electromagnetic fields, you'll see that this isn't too tough. We just follow the math and it'll all work out.